YouTube once we're done this afternoon. That seems to be popular for people who are sick. You can have a second look at this stuff. And I left off roughly here, where we said that epoxides are made by adding oxygen to a double bond. That's a very useful way of doing this. And we'll see today that this is a huge topic in organic synthesis, and it's become very important in terms of industry and how to put these things together. Let me make sure this thing's going to work. Epoxides are very important because they're easy to open up. They're strained, okay? There we go. We find that they're strained. They're quite easy to make, and you've got to recognize that, yes, you're introducing strain, but something else is getting better, right? To compensate for the strain going into the molecules, something else is becoming more stable. And in this case, it's the MCPBA that's losing its weak OO bond and therefore becoming more stable to give the epoxide. Now, we talked about stereospecificity. We talked about the idea that a cis alkene gives the product where the two R groups are on the same side of the molecule. And if you do that with these prochiral alkenes, you end up with racemic mixtures, because you can add from either side. So what we'll do today is very quickly just a bit of FYI stuff, talking about where these things show up and this Nobel Prize winning stuff in the past few years. And you'll get an idea of how important epoxides are, for example, in the pharmaceutical industry. So we talked about this. We'll deal with more of these things later when we talk a little bit about biochemistry at the end of the semester. And we'll find that epoxides do show up in nature. You will see them in biochemistry if you take that later on. And you can see here, we don't use MCPBA in biology, obviously. We have oxygen, we have enzymes to be able to carry the reaction out. And this is a very useful way of getting rid of material from an organism. It's a way of expelling material. You see that this thing is very non-polar, so how do we make it polar? We introduce oxygen, and for this example is an epoxide, and then we open this up to make this diol. This diol itself is quite polar, certainly more polar than what you started with, but then you attach it to a carbohydrate. Glucuronic acid is very polar. You attach this to that molecule, you get a much more polar material, and then you can eliminate, for example, in urine. And we'll talk about that in more detail later. What I want to talk about today to start off with is FYI. You're going to see this maybe in the future on a standardized test and that, so we need to talk about it. But the mechanism is very, very complicated, so we're not going to do the whole thing. We can see now that if we add simply MCPBA to an alkene, and your alkene has two sides, a top or a bottom or a front or a back, there's very little differentiation between those sides. And if your starting material is prochiral, you end up with racemic mixtures. And that's only so useful, right? We saw last semester that racemic mixtures can be a problem when we talked about thalidomide and the problems that caused in medicine. And now if you have 50% of your material is the wrong isomer, if you want one particular isomer and you end up with two, what happens to the other one? It's a waste, right? So people are developing chemistry to get around this, to try and make reactions selective, either diastereoselective or enantioselective. And the one reaction I'll talk about today is the Sharples asymmetric epoxidation, which won the Nobel Prize in, it's been a while by now, actually, it's about 13, 14 years ago. But it was a big deal because this all of a sudden made these types of compounds accessible in almost enantio-pure outcomes. So you can see here just this general picture that's showing the idea of a catalyst. We've got a lot to talk about catalysts in the near future. This idea that if you don't have a catalyst, typically the reaction is slow. If you put a catalyst in and you have some mechanism to go through in a lower energy pathway, typically the mechanism changes and you can get a reaction to go faster. So the one I want to talk to you about today is this mixture developed by Sharples and his group. He was at Wisconsin for a while, I think, and then he's at Scripps now out in California. And this kind of stuff, if it's Nobel Prize winning chemistry, it's obviously very, very clever and very, very useful. What you can do here is take what we call an allylic alcohol. It's a double bond with a carbon next to the double bond with an OH group attached. And it seems to only work very well with allylic carbons. And the goal these days is to avoid that, not to have to use an allylic material. You can see now that that start material is flat, therefore it ought to have two faces and two sides. So the trick is, how do you make the sides different? What can you do in that reaction to make this side different? Okay, this is not going to work for me today, is it? Let me do this again. You need to try and make the two sides different, and to do that you need to put it into an asymmetric environment. Now most of you are going to take biochem in some form or other, so you're going to see this type of idea. You take molecules that are flat, you put it in some sort of chiral environment, and you can differentiate one side from the other quite easily. Organic chemists are trying to develop these things, and we're doing a decent job, but we have a long way to go. And we'll see, hopefully here, there we go away. It's haunted. There it is. Okay. All right. You need to put this thing into some environment so only one face is actually accessible. And that's quite difficult to do. And this is a whole huge subject out there in organic chemistry about covalent or non-covalent bonding or binding to molecules like nature does and mimicking nature to get selectivity. So keep in mind, if we just use no catalyst and we use no chiral environment, we get a 50-50 mixture. We get a racemic mixture, alpha D is 0. And if you're trying to make one compound and not the other, you've wasted half your material. So in this type of reaction, Sharples came up with these compounds in which he was able to talk about making, there we go, titanium derivatives. And titanium is a Lewis acid. It's like aluminium, it's like boron, it can accept electrons. And his chiral environment was brought about by using these diethyl tartrate derivatives. And you can buy these things in bulk, and they're quite cheap and quite easy to get hold of. And they are pure. Okay, they're natural compounds that are formed, and you get the enantiomers as separate. Okay, so you can take either one of these, either the plus DET or the minus DET, and mix them with this titanium isopropoxide in the presence of the allylic alcohol, and all of a sudden you get very, very high selectivities in terms of enantiomer purities. So the mixture there involves titanium isopropoxide like that, and one of these, not both of them. Now the mechanism is complicated. You can see here what people think is the actual intermediate species. That's pretty complicated, right? People are still not quite happy with this, but that's where we think we are. The titanium gets hold of two molecules of the DET, and it forms this environment. This environment happens to be chiral. And then at the top, you can see that the allylic alcohol also binds to the titanium. You've seen things like this in freshman chem, where you get complexes and coordination chemistry. So in this case, the alcohol is pointing towards the titanium, and that sets up one face of the double bond being back towards the catalyst and one face being pointed out. So it's simply being blocked. The back face is being blocked and the front face is accessible. And then we have some epoxidizing reagents, some peroxide, for example, that can come in and deliver from one face. You're not going to see this in the class, you're not going to see this in terms of a mechanism, but you are to be aware of it in the future. Okay, this is where we're at. So here's what you can get. And I use this to show you what organic chemists are up to and how we're trying to mimic nature. Nature can get 100% in terms of the outcome. We're getting up to 98, 99, 99.5. And EE simply there, EE means enantiomeric excess, means that you get a lot more of one isomer than you do of the other. Okay, so EE, enantiomeric excess, 98 is great. You know, for a system that's been developed in the lab, that's fantastic. But it's not perfect, because you might still be getting 0.5% of the other isomer, which you still have to get rid of. And what's the problem with enantiomers? How do you separate enantiomers? Can you simply separate enantiomers? You cannot, because they have the same properties. So now you're into this idea of trying to develop pure material. Think about thalidomide and the problems that it caused in the past. And if you're trying to develop just the synthesis of one enantiomer, even 99.5 requires some separation and some purification, if your other enantiomer happens to be deadly or happens to be a problem. So this is a modern sort of idea. This is what people are up to in the business, trying to make these reactions go for them and make them go in very high enantiomeric excess. If you choose the plus environment, you get this particular isomer. If you choose the minus environment, you get the other isomer. And you'll see in biochemistry, a lot of this idea is based on a chiral environment in which the molecule sets itself up, binds to the chiral environment, and blocks one face over the other. So really that's all I want to say about that. The chemistry, the mechanism isn't in the textbook. The mechanism is way beyond the scope of the class, but this stuff is out there. Now, what I do want to talk about, and this is the bulk of today, is the reactions of simple epoxides once you've made them, because they are very, very similar to ketones and aldehydes in their utility in making bonds. In recitation, we've been pushing this a bit further with more examples and talking about synthesis and how to think about retrosynthesis and how to put a molecule together. This will now complement that. So epoxides are strained, we know that. And we're going to see two different systems. We're going to treat the epoxide in a basic environment and see something happen, and then we're going to treat it in an acidic environment and see a similar thing happen, but a change in what we call the regiochemistry. So what was regiochemistry? Region, where things happen, right? So we're going to see regiochemical differences in the two possibilities here in the two reactions. So in our first example here, we have a basic pH. And as we develop the course further, it's absolutely essential that you be happy with what this means, basic pH. So how much acid is there if we have a basic pH? No H+. And we'll reiterate this again and again. If you identify your conditions to be basic, in other words, the pH is greater than 7, all your intermediates will be negatively charged. I'll point that out again and again. It's just a nice way of keeping things straight. If you identify the material to be acidic, and you're doing H plus type chemistry, all the intermediates tend to be positive. It's a nice simple way of keeping things straight. Okay, this epoxide is strained. It's the simplest one we have, ethylene oxide, and we're treating it with sodium hydroxide. By now you should be thinking, all right, pH 9 or 10, high pH, no H plus. If I do need a proton, where can it come from in that mixture? Water, right? Water's the only source. You do not have H plus in there. And people will make that mistake. They'll start thinking, all right, I can put H plus in here, but all H plus will do is neutralize your base. Yeah, it's going to screw up your chemistry. So in this flask, we have mixed the epoxide here on the top left, and we're mixing it with sodium hydroxide in water, and it turns out we get this material. So what type of compound is that? That's a diol, right? It's a diol, and in this case, it's one next to each other, so it's a vicinal diol. It's actually ethylene glycol, which is antifreeze, and this material is opened up, to give the diol. So mechanistically, by now, people should be starting to see this without necessarily being taught it. You should be able to think about how this works. You have a base. Do you have any particularly acidic protons on that molecule? No, you do not. Okay? So a base is also a nucleophile. So if you don't have the possibility of an acid-base reaction, chances are you'll get a nucleophilic type of attack. So do I attack on oxygen? Does it make any sense at all to attack on the O? No. O is electron-rich with 2 lone pairs. Here you have a base with 3 lone pairs. They're going to repel. So you're going to attack the place in the molecule that has the delta plus possibility. And the delta plus possibility is on both of the carbons of this particular epoxide, and we can attack either one of them because it's symmetrical. So as you can see at the bottom, the mechanism is fairly simple. The base is acting as a nucleophile, and it's going after either of these 2 carbons and opening it up. Now be very careful. This does have a lot in common with carbonyls, and over the weekend when you put these things together, you can get lost. In a carbonyl, the carbon is bonded twice to oxygen. So when you push electrons towards carbon, you push another pair up to oxygen. It's somewhat behaving like a leaving group, but it doesn't leave because it was bonded twice. Right? You think about SN2 with a carbon-bromine bond. The carbon comes in, something comes in, kicks out the bromine leaves because it was only bonded once. Carbonyls are bonded twice. Same way with epoxides. This oxygen here is bonded twice to that framework. So yes, it serves the purpose of a leaving group. That looks an awful lot like it's accepting an electron pair like a leaving group would, but it is still stuck in that molecule. It's not going to break off because it's bonded twice. You're only breaking one bond. Now at the end of that, you have this alkoxide, and you're in a solution which has a polar protic possibility, so you have protons there which can be taken off. You do not have H+, but you have H delta plus. And so we can go ahead and do an acid-base reaction and end up with this diol. Yeah? There's nothing tricky about that. So epoxides are going to be very, very useful to look at a broad range of nucleophiles. The big thing we'll do today is give you a chart with a bunch of nucleophiles, which you've already seen, and then you can use them to open these things up. Carl? Yes, it's a good point. We're going to see that in a second. So bring that with you from last term. When we had the bromonium ion, and when we had the mercurium ion, and now when we have epoxides, you're going to end up with a sort of an anti-addition, yeah, from the back. Because what does this look like? It looks like an SN2, sort of a modified SN2 in which the nucleophile has to attack that carbon from a certain direction, and it's going to do it the same way. It's going to come in from the back, right? So that's a good point. Are we happy at the back? Okay. In terms of the utility of this type of thing, you can use all sorts of different nucleophiles, and we can see the possibility here on this chart of how useful this can be. Now, at the top, you've got the possibility now of looking at the reaction profile and thinking about why these reactions are so good. And the term has been used, particularly by Sharples, the Nobel Prize winner, that epoxides are kind of spring-loaded. They contain all this potential energy that wants to release. And so when you attack them, they open up, they pop open. Right? So they're very, very good electrophiles. And we say that they're spring-loaded electrophiles. Now, the chart at the bottom should not be of a concern if you'd be keeping up. You can think now about the possibilities of expanding the type of nucleophile that we could use here. Instead of just using O, how about you use C, or you use S, or carbon, or hydride, the nucleophiles that we've developed quite recently. So all this chart is showing you is the possibility of all these different types of reactions happening with alkoxide. We just did that one. We did hydroxide, that's the simplest example, but you swap the hydroxide, HO-, for example, methoxide, CH3O-, you should get the same chemistry. And in this example, you do. And again, you get the sort of anti-type of addition where the nucleophile comes in from the back and opens this thing up. And you can now produce all sorts of complicated molecules in which you have one ether down here and one alcohol up there. And like it or not, that's where we need to be, right? For polymer chemistry, for biochemistry, stuff like that, sort of polyfunctional type of systems. We saw this last semester. We haven't seen it a lot recently, but NaCN is a very powerful nucleophile. Small, can get to places quite easily. Very good at SN2 last semester. And in this example, what's happening is maybe a two-step process, or you could argue that this is in solution, so you have water in there, in which the nucleophile comes in, and it simply does the same thing. It goes after that carbon, and it kicks open, like so. The difference with the carbonyl chemistry, and I'm going to say this now so that when we get to the end of this section, it's not that confusing. All the carbonyl chemistry that we did, watch this, the nucleophile came in on the same carbon that was attached to O. So in the product, the nucleophile is attached on the same carbon that has the oxygen, as opposed to the epoxides, in which the nucleophile comes in and ends up on the adjacent carbon to the hydroxyl. Make a note of that. However you do this, make a note of that. If you're listening to me and memorizing this thing, go ahead. It'll be on the web later to have another look. You now have some versatility in making those bonds. If you're using a Grignard reagent with a carbonyl, it goes on the same carbon as the oxygen. You can't get around that. But if you want to manipulate this so that the nucleophile goes someplace else, use an epoxide, because it goes next door. You'll see that again when we get to the end of the chapter. So other types of nucleophile, we saw sulfide last year. S- is a very powerful nucleophile, even though it's quite large. It's easily polarized, it's good at this. And of course, Grignards should be very good at this. Grignards are also very basic, but we've already argued that there isn't really anything acidic in here, so the epoxide is going to be attacked, and you're going to be able to open things up. So all of a sudden, this one, keep an eye on that one. You have another potent, powerful carbon-carbon bond-forming reaction, but slightly modified to carbonyls because you can position the R group in a different place. At the end, what's LAH? Lithium aluminium hydride. What does it introduce? What's its nucleophile? Hydrogen, right? So you can open these things up and simply make an alkyl group. Pierce. Borohydride might work slowly, yeah. But LAH is the better option because it's a more potent reagent. So all we've done there is expand the universe in terms of what you can do, what you can use here. So we have some very powerful types of reactions. Just to sort of put this in context, we will go back in the near future and do this with carbonyls. We'll use these with carbonyls, right? We've done that with this, and we've done it with this, but we'll finish everything off in the next few weeks, where carbonyls then react with all those other species, and you can expand this sort of playing field in terms of what you can do. Leslie, you all right? Look a bit pensive. Okay. Moving along. Let's talk about regiochemistry. This is a big deal. In this system, your epoxide is biased. And by that I mean the two carbons that can be attacked are different. So now we have the possibility of regioselectivity. This is logical, right? If we're talking about SN2-like chemistry, what happens as the electrophile gets more bulky? What happens as the electrophile gets more crowded? What happens to the SN2? It gets slower. It gets slowed down. It certainly does. So when you're talking about the approach of a nucleophile to a molecule like this, which has two different carbons you can attack, if it's SN2-like, because it is basic, and the SN2 reactions always involve, or pretty much always involve anions, then looking at this type of compound, we should be happy with why the result is as it is. In this example, you've got this sort of isopropyl-looking thing. It's certainly a tertiary carbon on the left, and you've got the possibility of attacking this primary-like carbon. So it should be fairly obvious. If you can identify the fact that this is a basic reaction at basic pH, then the nucleophile is going to have a much easier time attacking there than it is attacking here. So if you identify the reaction as being in basic conditions and you have an epoxide opening, it's going to attack at the less crowded carbon, simply because it's acting like an SN2 type reaction. Nothing different to anything we've done in the past. In terms of utility, you can think about using this now to make some fairly complex systems. And as Kyle said, if you start out with an epoxide, you're going to come in from the opposite side. So this is taking that first idea from that slide and going a little bit further. You can see at the bottom, we have a cyclic system which is rigid, and the epoxide is on the top face. The first thing you have to decide is that this carbon at the bottom is more accessible than that carbon at the top. If that's the case, it's going to attack there. Now you have to worry about direction. And just like last semester, the questions always have this little bit at the end. take account of any stereochemical issues, any regiochemical issues in the system. Make sure you're aware of that, make sure you understand what that means. So in this case, we have, I think, both stereochemistry and regiochemistry. The regiochemistry is all about attacking there, because that carbon is less crowded, and the stereochemical outcome leaves the nucleophile trans to the hydroxyl, because it has to come in from the back. The epoxide is pointing up, just like in the SN2, the nucleophile has to come in from the opposite direction, and therefore we get a ring opening, and you get this, and it looks like it's been inverted. So that fits an SN2, right? All the language there is common to SN2, so if you come to that reaction, this isn't that much more difficult. Michael? Potentially you could have much slower reactions because of some conformational problems like that. Yeah, but we're using pretty potent nucleophiles here that will get the job done. Anybody? Mr. Davis, how you doing, mate? You all right? Oh, he spoke again. That's great. It's like every day he speaks. Wow. Mr. Owiniak, you all right? Mr. Ryan? Whatever. Okay. Moving on. So be able to identify the type of reaction conditions. That's the very basic requirement right there. Obviously, we need examples. We need to be able to put this into practice, either in a synthetic sense or in a mechanistic sense. And then for next week, retrosynthesis, thinking about how to design a molecule. You're given some starter materials. How do you put this complex molecule together? That's really important. So we start off here with a simple alkene. And the system here is biased because it's not symmetrical. So we can expect some interesting possibilities when we put this thing together. When we add MCPBA, what type of molecule do we get? It's going to be an epoxide. The first thing you'll make is an O here, the pi bond goes, and you'll make that, where there's no pi bond. Now, racemic or just one molecule? I think it's racemic, isn't it? So we'll put, all right? I'll put plus minus to show it's racemic. Be very careful with those little details. Now, pH-MGBr, what do we know about that? Give me some ideas of its characteristics. What do you know about pH-MGBr? What's it good at? It's Grignard, I agree, it's a Grignard. But what's it good at? It's good at being a Grignard reagent. What are Grignard reagents good at being? Nucleophiles, thank you. It's a very powerful nucleophile, it's also a very powerful base. So if you have acidic protons around, you're going to have problems. Let me do that again. If you're going to have acidic protons around, the nucleophile will get quenched, but if you don't, it'll be a powerful nucleophile. Very quickly, is that basic or acidic? It is basic, right? And I say quickly because as we progress through the semester and things get more complicated, that's the very first decision you must make, and that really sets up the tone for the mechanism of the question. So in that case, yes, it's very powerfully nucleophilic, and we have a choice of attacking at two positions on that carbon, on that epoxide. Where will I attack, the left carbon or the right carbon? The right carbon, because it's more accessible. So the mechanism, if that's being asked, is simply pop in the nucleophile, open up the epoxide, and that gives me O- right here, and this last step. I've been using this in recitation. We've got some examples of it here so that everybody sees it. NH4Cl is basically HCl. It's a toned down version of HCl. The problem is if you make O- and an alkoxide, it's very, very basic, and if you dump in acid, HCl, it's very, very exothermic and it can be dangerous. So we dump in NH4Cl, and that's not so bad. So that's going to be our source of acid, and that will give us ultimately the quench material in which we have a racemic mixture and a very much more complicated product than where we started. So it's very useful. I would argue that epoxides are as useful as carbonyls. If you understand the carbonyls that we've been doing, epoxide are about the same. Okay, next example. I'm sorry, there's the mechanism. We did that, we talked about SN2 control, and let me point out that term actually while we're here. You'll see this in the textbook. SN2-like control. Without giving this away, guess what happens with the acid? This is all about basic and all about crowding and approachability and accessibility, which govern the SN2 under basic conditions. And we're saying now that this is SN2-like. What do you think the switch is for the other epoxides in acid? SN1-like. Why not? It will exactly be SN1-like. So you understand the SN1 and the SN2, these reactions aren't particularly tricky. So, moving along. Another example. In this case, MCPBA, again, is going to give you the epoxide by adding to the pi bond. And then, again, the question will be, is it one single molecule or is it a racemic mixture? It's racemic, right, because you have prochiral starter material. And then we can bring in whatever you want. You know, that phenyl group could be replaced by a methyl, an ethyl, a propyl, an elephant, whatever you want. Any type of grignard, anything with a bromine attached, you can make a grignard from, and you can bring that thing in. It's the same chemistry. You understand that. This isn't that tricky. So with that in mind, there's the product. We should be happy with the regiochemical outcome. The phenyl group went to the more accessible carbon of the epoxide, and then we get this trans stereochemistry because of the approach from underneath. It's an SM2-like reaction, so we ought to get inversion. In terms of a more complex system, this is where we go. If you understand the basics, there's nothing tricky here. In this system, we've already got this. I'm going to use magnesium here. Let's swap this out for cyclopropyl magnesium bromide because we haven't really seen lithium reagents yet. This would be cyclopropyl group with a magnesium bromide attached, and THF is a good polar aprotic solvent. So again, the question will be, where will this thing attack, left or right? The right-hand side because it's more accessible, and then we quench, and we end up with this. And we get a much more elaborate product by doing very simple knitting. You're knitting things together. If you can knit, you can do this stuff. Can you knit, Gotham? Learn to knit. So you can do organic chemistry. It's that straightforward. Now, change the molecule. Seemingly a different problem. This is why people get lost in this subject. It isn't a different problem. It's the same problem. Obviously, the structure is different, but the ideas are the same. The epoxide, again, is biased. It has different places it can attack, and we're going to go for the less crowded material here, less crowded place, and the nucleophile is going to come in on this carbon because it's less crowded, and we end up with that. Anybody got anything to say? Richard Stanovsky. On this example, it's a fine point. Yes, there's no stereochemistry shown in the starter material, but this atom down here, yeah, this is going to be chiral, isn't it? Yeah? You'd have to show it with the wedges and dashes to be able to assume that. But yes, you're going to get chirality in there. So if we're done pretty much with the basic conditions, we move on to the acidic. And this gives you flexibility in where you can do your chemistry because the regiochemistry changes. So just to review that very quickly, and maybe make a note if you're finishing this off. Identify basic conditions for an epoxide. It'll open up like an SM2 reaction. You'll get attack at the less crowded position. And that can just be summarized as SM2 control. Moving on to the acidic conditions. We changed the pH. We're now talking about protons. We're not talking about hydroxide anymore. This thing is not basic. This thing is acidic. All your intermediates now will tend to be positive instead of negative, and it will be a different type of process, different type of mechanism. So we have some species that you should be able to identify as a powerful acid, HCl, HBr, HI. And we find out again that we get a ring opening process. Starting out with ethyloxyrane, the simplest example, we can work out the mechanism very easily. And what do we think the first step is here? Proton transfer to the O, because it's basic and it has lone pairs. So let's do that. And that should give you some species in which the O is now positive. And what's so good about making an O positive? Good leaving group. Good answer. It's a good leaving group. Now be very careful because we're mixing, this is subtle. It's a good leaving group, but does it leave? No, because it's bonded twice. You can use the same ideas. Starting at the bottom, we just protonated the epoxide and we got this alkoxonium species. I'll be saying that a lot. So this protonated OR group, which can break off if it's singly bonded, or it can open up if it's bonded twice. So now the nucleophile, what's left over? Br minus, I minus. They were good nucleophiles, right? Which was better, I minus or Br minus? I minus. Less electronegative, more easily polarized, better nucleophile. So we can get attack. Again, the motivation here is to break open that epoxide and open it up, or at least the energy involved. And that gives you this type of outcome. Okay? Now that looks like an SM2, doesn't it? That looks very much like an SM2. And that looks an awful lot like the synthesis of N-butyl bromide that you did last year. Because it's a primary-like carbon, which is unlikely to open up. But this will modify, this will change as we start putting R groups on these carbons. So the very simple system, I think we should argue that this looks like an SN2 reaction because the carbons we are attacking look like they're primary. Okay? Does anybody think that that will open up into a carbocation? I don't think so either. right? Because you'd put the positive charge on a primary cation, and that's not good. What stabilizes carbocations? Hyperconjugation, which is sharing electron density from adjacent single bonds. The more of those bonds you've got, the better. We don't have any down there. So here's a couple of examples of how you can use this. Change the pH, make it acidic. The mechanism changes, the outcome seems to be similar. So at the top, acid, sulfuric acid maybe, phosphoric acid, something that does not have a strongly nucleophilic counterion, and you protonate and you open up. So you have another avenue to making these diols. At the bottom, you swap out the water for an alcohol. You got the same idea. The nucleophile now is the OH group on the R, so it's a nucleophilic alcohol, and we can open this thing up and make these types of materials. That's pretty straightforward. That fits the same picture that we just dealt with, even though the pH has changed. There's the mechanism for that. There's the sulfuric acid coming along, the proton transfer. There's the water behaving as a nucleophile, and then the water comes in and takes off as a base. If you're memorizing this, you're going to have a really bad headache by next week. If you're understanding this stuff, it just falls into place. And I've had some people make comments this week that, wow, some of this stuff really is starting to come together. And that is great because it makes it's less painful to learn. It's more fun to learn. So you can make ethylene glycol very easily by that mechanism, by that process. Now, everything changes when you put R groups on the epoxide. Because now, what happens to SN2 when you start to put some bulk on there? You slow down. And if, let's say for a tertiary system, the SN2 wasn't possible, what could take over? What could operate instead? SN1. We had a shift, didn't we? Right? The secondary systems are always the problematic ones because they could sometimes do SN2 and sometimes do SN1. But you have the two possibilities. Likewise here, you have both possibilities allowed. Now, looking at that system on the left with the methyl group sticking out and looking at the possibilities here, we just dealt with nucleophilic attack in an SN2 sense, where the nucleophile prefers to go for the less crowded carbon. And for most examples, that's the case. But now, when we get to the tertiary systems, we're not going to be able to attack that carbon with an SN2, right? But we have the other possibility. We have something more interesting and something subtle that allows the switch in regiochemistry. So the nucleophile doesn't attack at the less crowded carbon, it actually goes to the more crowded carbon. So we've got to understand that. When we protonate this species, it's on the next slide, but I'll get it started with here. Right, there's what we're going to make. And in particular now, I have two systems, two carbons, one of which is primary-like, one of which is tertiary-like. This atom, this molecule, is very much like H3O+. I always refer back to this because it works. Okay, you learn that, hopefully the first day of any chemistry class you take. Now, we always draw the plus charge on the O, because formally, it has fewer electrons than it started out with. It's shared a lone pair with the proton to give you H3O+. But when we build up a more sophisticated picture, where is that plus charge? It's on the hydrogens, right? That positive charge is spread or shared by each of the hydrogen atoms. In the organic class, we get this little delta plus idea to show that. So that explains why a base goes after the proton, right? And not the oxygen. The base goes after the electron poor species, which is the proton. Now, you've got an oxygen in the middle, highly electronegative. If you make it positive, what do you think? More electronegative or less electronegative than neutral? More, way more. Very positive oxygen is very, very electronegative. So take that further to this molecule. We just protonated an epoxide, and we're asking the question, all right, is it the oxygen that's really positive? And the answer is no. You have carbon next door with an electronegativity of 2.5, and a super electronegative oxygen, which is pulling electrons away from those carbons. Where would you rather put delta plus? On this tertiary carbon on the right or this primary carbon on the left? Tertiary. You would rather build up a significant positive charge right there. And in some instances, you might even break open that epoxide and make a carbocation if it's stabilized enough. That's more of a sort of a graduate idea, but that you can do. So what we're going to say here is yes, the nucleophile will go there even though it's more hindered. But there's got to be more to it than that, because that kind of breaks all the rules, right? The idea is that that molecule doesn't look exactly like that. That bond is significantly longer than it looks because the oxygen is trying to break away. Let me see if I can do this on the next page. Here we go. This is key. If we've protonated the O is not happy. It wants its lone pair back. Okay? And it's going to take it away from one of the two carbons. Brock the Angelo. Yes. 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 Because if you think about negative conditions, basic conditions, you'll be making O- and C+. That doesn't work. That's too unstable. If you protonate the O, we've always said that's a way of making that a better leaving group. And we can now think about the possibilities here, because guess what? That system is strained. This molecule is strained. It wants to open up. So you could argue maybe even that this bond will break before the nucleophile comes in, because you'd make a carbocation here. And what kind of carbocation would be formed if I break at the right? Tertiary, which is pretty good, right? You've made those yourself in lab. If you break open on the left, what type of carbocation do you get? Primary, horrible, not going to happen. Well, for most of these examples, it's somewhere in between. It's not the molecule breaking apart, but it's trying to. And that's shown by the structure on the right-hand side. The oxygen wants its electrons back. It's going to pull electron density away from both carbons. It's going to take more electron density away from this carbon on the right, because that's tertiary and it can handle it. The alkyl groups are pushing electron density towards that carbon. You're taking electron density away. The alkyl groups can compensate. So this is said to be SN1-like. The nucleophilic attack is going to occur on the right-hand side of the molecule here, because that's where more of the positive charge is. As simple as that. Now, if we go on, Brianna, then you're going to get an attack of both. You get an attack of both, or it could be an SN1 more likely to be an SN2. That was always the grey area last year. Okay. In this example where it's definitely biased, right? You have a primary versus tertiary, and that was always straightforward. It was either SN2 for the primary, it was SN1 for the tertiary. No arguments there. This molecule now, they're the same thing. That bond is longer than this bond here, because that molecule is trying to break apart because the epoxide is strained. That's okay. Now, how can I all of a sudden attack a tertiary carbon? Why is SN2 so slow on a tertiary carbon? It's crowded. And what shape is a tertiary carbon typically in an SN1 reaction? In an SN2 reaction, what shape will the carbon typically be? Tetrahedral. Now, what tetrahedral is 3D, right? Tetrahedral has things pointing away from the carbon, so the nucleophile gets blocked. But what's happening here? If that's looking like it's becoming a carbocation, what shape is it trying to adopt? That kind of gives it away, doesn't it? I shouldn't do that when I do this. But what shape is that trying to show? Flat. That carbon is significantly flattened compared to the picture on the left if this is real. And if it's flat, even if it isn't purely a carbocation, it's easier to attack. That's okay? Leslie, you're nodding your head in a positive sense. Yeah, not looking horrified. Good. So we're going to argue that the nucleophile will come in here instead, because that is now accessible, because it's flattening out, and that's where the positive charge is and where the nucleophile is needed. John. Well, the tertiary allows the stretch. That's exactly right. Okay. The argument in the first semester is always that primary systems will not allow for a carbocation to form. So that precludes the SN1. So they do SN2 instead. And the flip argument to that is because they're accessible. The tertiary on the other side, which is exemplified here because you have the extremes, primary versus tertiary, the tertiary isn't very accessible. That's why typically the SN2 doesn't work. But it allows a carbocation because tertiary carbocations are stabilized by hyperconjugation, right? This is somewhere in between. Now in these examples, we can see the exaggeration, primary versus tertiary, and the fact that we have a strained epoxide. That epoxide is wanting to open up. The picture on the right, this whole thing, is showing that trying to happen. The thing is trying to open up. So that results, even before the nucleophile comes in, the nucleophile isn't there yet, even before the nucleophile comes in, that carbon on the right-hand side is bearing a significant amount of positive charge, which is only possible if it's tertiary. Now, I've recorded all this, so if that didn't make any sense, hopefully we can go back and you can read it again or listen to it again. But that's where we're at. Mr. Homan. No, this is going for the tertiary carbon. You get selectivity. Right? This is... It looks like you're going to get inversion in that process. So now, I'm not going to say this out loud, but maybe this is like an SN1 with inversion. I did not say that. I didn't. Mike Idacoli. Well, there are examples. Take my graduate class, take one of the advanced classes, right? You'll see that if the carbocation is stabilized enough, for example, by resonance as well, maybe you get the carbocation. And the evidence for that is the stereochemical outcome. Because you can get racemic mixtures even from things like this. There's a lot of grey stuff that we are not talking about. I'm being very careful not to say these things out loud. I will edit my video. Okay? Got to be very careful how we say these things. But this is a switch. And that can be useful because you've switched where the reaction can happen. We'll do more of this later. If you want to go for the less crowded carbon, do an SN2. Use a powerful nucleophile under basic conditions. If you want to go for the more crowded carbon, set it up with acidic conditions so that it opens up like this or tries to open up like this, and then you can attack at the more crowded carbon because it's flattening out. You're right, Sam. You like that? Poetic, wasn't it? Don't ask me to do it again. Watch it on YouTube. Okay? So there's the argument. You've got to get your heads around that, and there are more to come. Many more of that. All right. So what we need to think about here, I think, is maybe some examples and think about summarizing that stuff so that we have something to take away. Here we can see on the left, in acidic conditions, very much like the switch from SN2 to SN1 last semester, which always was a problem with the secondary carbons, it's the same here. It's a problem with the secondary carbons. Because secondary is accessible, but the carbocation is okay. So they can do both depending upon the conditions. And here's the fact. On the left, if you protonate the epoxide, you can attack either on the left, which is primary, or on the right, which is secondary. Now, there's not that much of a difference between primary and secondary carbocations, right? There's a huge difference between primary and tertiary. That's why we had that argument just now. In this example, in acidic conditions, on the left, the SN2 prevails because the secondary carbon can't hold that much of that charge. We don't get the outcome that we just saw. So that's called a steric effect. That's all about SN2-like. As opposed to on the right-hand side, and this is key, there is a definite difference, completely in line with what we did last year, in which the primary system can only go SN2 and the tertiary system goes SN1. Right? So that requires an electronic effect. And the electronic effect here is the fact that in that protonated species, that carbon is significantly positively charged. Maybe it's not a full carbocation, maybe like the bromonium ion last year. The bromonium ion was a stabilized carbocation. It's not fully open like a carbocation, but it is, or it does have carbocation characteristics, and therefore can be flattened out. And so this attack isn't unbelievable. You're not attacking a true sp3 tetrahedral shaped carbocation. You're attacking a flattened out, somewhere between sp2, sp3 as it's changing, carbocation that's accessible. And that is useful because you can switch where things go in your molecule. Now at the bottom, there's an example. Okay, I think Nate was the one who said something about inversion. If you look here, on that particular example where you have a choice, that particular example at the bottom where you have a choice of attacking here on the left, at the bottom, or here at the top, it looks like it's actually going at the bottom. That's because it's a tertiary system, and we're going after that because it can accept positive charge and be flattened out, and therefore we can attack there. But also because the epoxide's at the top, the OR group's coming in from underneath. Isaac Napoleon Pierce. Well, that's right. That's there, isn't it? Right there. That's that one. The tertiary wins. The tertiary will go SN1. Yeah? The tertiary will go SN1. Nate? What you said first. Yeah, because this one, I mean, I'm going to say it out loud, but I don't want to scare people. This one is SN2-like and SN1-like. You won't like medical school if you can't handle this stuff. Kyle. In this example, it says, the fact there in that experiment is that you get an inversion. But, you know, just to sort of whet the appetite if people are interested in this stuff in the future, what if you put something here that's conjugated? What if you make this conjugated and you put some pi bonds there so you can help stabilize a positive charge? Maybe then it can open up, right? But that's intermediate organic 5821 in the fall, or advanced organic 6941 in the fall, right? So, you know, don't forget that the title of this class is Introduction to Organic Chemistry. We've got to be very careful that it is just the tip of the iceberg and an introduction. But if you're interested in these things, we've got plenty of classes you can take to learn them. But I'm glad that people are asking those questions because you're starting to think like chemists. And everybody should be a chemist. Well, that's my argument about epoxides. I'm going to mention this because I've got a couple of minutes left and I hate wasting time. But I'm almost done with this chapter. This is sort of a, you know, get on it quickly because I'm about to go mad. We're going to start spectroscopy on Friday. And spectroscopy is notorious for losing people. All the chemistry we've done so far, you know, we're pretty much done with chemistry. The rest of the week before the exam is all about physical methods to determine how you know what you've got. How do you know you have an alcohol? How do you know you have a carbonyl? You do this in lab next week. It's the experiment in lab next week. So you'll do it as you're actually learning it. But before we get there, we'll spend a few minutes talking about these things. The sulfur analogs of alcohols. And these things are very useful in biochemistry for nucleophiles. We'll do some of that later. But they have very similar properties, except they stink. Right? These things are notorious for absolutely stinking. Skunk, apparently. If you smell a skunk, you're smelling some sulfur material. Nasty. If you smell natural gas, you're not smelling natural gas because natural gas has no odor. But you're smelling butane thiol, which is a 4-carbon chain with an SH at the end. You put that in there in very low concentration. You smell that stuff. You can smell that stuff. You know it's there. You know there's a gas leak, right? It's a marker. But we can talk about nomenclature. There's nothing much to this. I mean, the thiol, again, if you're taking biochem or polymer chemistry or anything in the future, you need to know these things. Thiol, sulfur, that's the clue. 3-methyl-1-butanol and 3-methyl-1-butane thiol, they're cousins, obviously. Okay. We'll talk about putting 2 of them in there. I'm not that interested in this just yet, but the other abbreviation for sulfur is mercapto. If you see mercapto, that also indicates that you have a sulfur in a molecule. And the mercapto group itself is the SH molecule, or the SH group. Now, how do we make them? This is straightforward stuff, which we have done in the past. Thinking about what we just discussed, which was quite complicated, let's get back to something simple. Strong nucleophile, primary alkyl halide. What mechanism? SN2 all day, every day. Okay? SN2, nucleophile comes in, bromine comes out, and you can make a thiol. That, in fact, is 1,2,3,4 butane That's the marker that we use in natural gas to make sure you can smell it. Next one down. Why is this inverting? Why is the stereochemistry changed? It's an SN2. Think again backwards. That's an example of an experiment you can do to prove it's an SN2. The product was inverted, therefore it must be an SN2. Okay, so we'll leave it there, and then Friday we'll finish that off. And be here Friday. If you're not here on Friday, you're really missing out.